Introduced me, I'm here to talk about extending containerd. And just a little bit about me, I'm an engineer at Amazon Web Services. I've been working in the container space for about the past 5.5 years. And I just want to give you a brief overview about what we're going to cover today. We're going to just first dig into a little bit about what containerd is and why I think it's interesting. We're going to talk a little bit about containerd's architecture and how it's designed in a very modular way. We're going to cover the different extension points that are available for customizing its behavior. And then we're going to have some examples and a little bit of a demo. So the first thing that I want to talk about is containerd itself. I hope that if you're at this talk, you're at least somewhat familiar with containers. Maybe you've heard of Docker, maybe you've heard of containerd. I'm going to be talking mostly about this containerd runtime today. It's maybe a little bit less known container runtime. It's small and focused, has a very limited scope in terms of its design so that it remains very simple. It was built by many of the same people that put Docker together, and they used lessons that they learned from things that worked well in Docker as well as things that were not quite as good in Docker. And so one of the things that makes containerd different is its limited scope, its strict subset of features that it's going to support. So some of the things that it does do are it does container lifecycle management, it does image management, it manages the container standard I/O streams, but it doesn't do things that are higher level functionality, things like overlay networking, having networks between multiple different machines. It doesn't do clustered storage, so anything with storage where you're sharing between different machines. It also doesn't have any built-in logging features or log collection things, log aggregation. So instead, it's just limited to the basic functionality around how do I run containers and run them well locally. And it's built as a bunch of modular composable pieces that are meant to be extended, and that's the main thing that we're going to talk about today. One of the interesting things about containerd is it's designed to replace some of the functionality from Docker. So it is used by Docker, and Docker uses parts of it, but not the whole thing. This modularity allows Docker to gradually move over to the parts of containerd that are available. And over time, that amount of containerd that Docker is using has gone up. It also has modularity that allows for new use cases that are not imagined by the original authors of containerd. And some of the examples that we're going to touch on today are new use cases that were not originally part of containerd's design. But before we dig into that, and before we dig into some of the architecture, I want to talk a little bit about images and layers first. So container images are representations of a file system. Docker popularized this concept of a layered image, an image that consists of multiple different parts that are put together to make one union file system. Images are stored, and how images have a copy-on-write view of the different files that are present in the file system. So you can see 3 different layers here. There's a bottom or a base layer, which has marked as read-only. There's a middle or an intermediate layer, which is also read-only. And there's a top layer, which is marked as read-write. If you look at the diagram, you can see that there's a few files on the bottom, there's a file in the middle, and then another few files on the top. And there's some connecting arrows here that are trying to show you where the files are coming from. So if you look at the file that's in the base layer and it's connected by the green arrow to the top layer, that's a file that is unmodified from the base layer and is visible in the top layer without being copied there. In contrast, if you look at the one that has a blue arrow, there's a replacement in the intermediate layer. So it hides the original copy of the file that's in the bottom layer, and the top layer only sees that replacement. There's also in the top layer a brand new file that's not present in any of the other layers. And finally, there's a file there with the no sign that's a deletion marker. So the middle layer is hiding that file from existence. The top layer can't see it at all. The properties of how these work give you copy-on-write functionality. So when you open a file for writing, it gets copied up into the appropriate layer, and it can be modified. But this gives you efficient storage for sharing layers between container images and sharing layers between containers. The way that it typically works when you're running a container is you allocate a new empty read-write layer on top, and only the files that your container is going to modify end up being stored in that layer. So the reason that I wanted to talk about how images and layers work is because the first 2 pieces of containerd's architecture that we're going to talk about are relating to images. So there's a diagram up here about the different parts that make up Containerd's architecture. And these are independent pieces that are meant to work well together, but they can also be composed and replaced and used separately. So we're going to dig into a couple of them that are related into images first. The first one is what's called the Containerd content store. This is where raw image content is stored, or the raw layers. When you go and pull an image into a container runtime like Docker or Containerd, it's typically pulled as a series of compressed tarballs or compressed archive format that's not directly usable on disk. It's going to have to be extracted, it's going to have to be written into the file system somewhere, and there may be some sort of transformation step that enables the copy on write functionality to happen. The content store isn't really concerned with that. The only thing that it stores is the original archived copies of the layers. The next part of being able to actually use images and use layers is being able to lay them out on disk and interact with them in that copy on write functionality. And that's the role of the snapshotter. If you've used Docker before, you've seen what it calls its storage or its graph drivers. The snapshotters are basically the same set of functionality. The final bit of, one of the final bits of Containerd that I want to talk about is how you actually run containers. Containerd dispatches to a lower level container runtime. This is something that is responsible for actually starting up the processes that make up a container and configuring the parts that are necessary for it. The default that Containerd uses is something called runc, which is the reference implementation of the OCI runtime standard. Runc implements Linux containers, and it does so using a bunch of primitives in the Linux kernel, things like cgroups, namespaces, seccomp capabilities, and so forth. Containerd supports a couple different kinds of runtimes. So one is that it supports any valid OCI runtime, anything that adheres to the same interface as runc. And it also has its own separate version 2 of a runtime interface. The last bit of Containerd that I want to talk about is the gRPC API. This is the central interaction point for Containerd, and it's responsible for mediating the interaction with each of the different parts that make up Containerd. The typical use case for using Containerd is by a higher level program, not interactively. And so the main design is around this API and how that higher level program can interact with it. There's also a higher level client library that's built on top of that API that coordinates actions between different parts of the Containerd API. And is responsible for implementing common workflows, things like pulling images and running containers. So Containerd's overall architecture is that of a modular core built of small separate services that are designed for extensibility. And the way that you use it is that you use these different parts together. Interactions are typically modeled as interfaces in either the gRPC API or interfaces in that higher level client library. And there's a set of plugin mechanisms or extension mechanisms that make it easy to customize the behavior when you want something a little bit different. So now that we know a little bit about how Containerd works, we can talk about the extension points and where it can be customized. So there's 5 basic extension points for Containerd. There's a thick client library in Go that we talked about before that models interactions as interfaces. And you can swap for different implementations inside the client when you want to have different functionality. There's also what I like to call command line or executable plugins. These are programs that Containerd executes for you, and you can configure Containerd to run a different program in place of the one that it runs by default. Containerd also supports gRPC proxy plugins, which are, again, separate programs that implement an entire set of Containerd's APIs, and Containerd is able to delegate out to those programs when it needs to invoke that functionality. Containerd has the ability to load dynamically linked Go plugins. And if you need something even more powerful than that, you can build in your own compiled plugins into Containerd, and you can have your own version of Containerd. So I'm going to talk through each of these. First thing that I'm going to talk about is these client library extensions. So Containerd is built for programmatic interactions, and it has this smart client or thick client in Go that models a bunch of the higher level functionality that most clients are going to need. These are things like being able to pull images into Containerd, or being able to run containers or manipulate them in certain ways. These common workflows are modeled as interfaces in the client library, and they can be swapped out for different implementations when you need something different. So I want to dig into the pull workflow. Containerd is a little bit different from some of the other container runtimes you might have seen. For example, Docker has a simple pull API, and then Docker goes and does all of the networking for you to make that image appear locally on your system. Containerd doesn't do that. the actual containerd daemon itself doesn't really know anything about the network. Instead, polling happens as part of a workflow in the client library, and it's the responsibility of the client program to handle all of the things that are involved in making the image appear locally. So there's a default implementation in that client library that can handle talking to Docker registries or OCI registries, and that's what most people are probably going to use. It's what most people are probably going to need. But it is easy to customize if you need something a little bit different. For example, if you want to have Docker-style bare image names, like I want to pull Redis, but you don't want to pull it from Docker Hub, you can define your own implementation of the puller in here to go and resolve that from your own network location that is not Docker Hub. Or you could do things like, I want to customize the TLS settings or the timeouts that are involved in the network transfer. Or if you want to have some completely different protocol, like implement something with BitTorrent, you can do that as well. One of the things that I've done at Amazon is worked on an implementation for Amazon ECR, which is Amazon's container registry, and exposes its own API that's a little bit different from the Docker registry API. And so we're able to write something that takes advantage of the way that ECR works and makes it a little bit faster. So what I'm going to do next is show you a little bit about what the code looks like. So this is how you can write some code to pull an image using the default implementation in the containerd client. You can see there's that client object, and there's a pull method on it, and there's a few arguments in here, like the name of the image that's being pulled, as well as something telling it that I want to unpack the image. But there's just a couple things here, and it's very simple. But it's also open for customization, and there's a reason that there's some empty lines here. We can go fill those in here, and you can change that to use a different resolver. That's the implementation of what containerd calls the thing that implements that pull workflow. So you can see here that the only real differences are I'm constructing my own resolver object, I'm passing that resolver to the pull function, and then I've changed the identifier for the image because this particular resolver requires that format for it. So it's pretty simple to go and swap out and use your own. But what does it mean to go and build your own? So this is what the resolver interface looks like in that client library. And this is the interface that you would implement if you want to go and build your own resolver for containerd. It has three different methods. The first one is the resolve method. This is responsible for returning a canonicalized identifier for the image, as well as what containerd calls a descriptor. The descriptor contains things like the expected digest of the thing that's being pulled and the media type that's going to be pulled. That's used in other parts of the subsequent parts of the workflow. There are also two other functions here called fetcher and pusher. Fetcher returns an object that knows how to retrieve content, and pusher returns an object that knows how to push content. So if you want to implement something that goes and deals with images in containerd and deals with remote registries, you would implement at least a fetcher in order to pull something. And if you wanted to be able to push as well, you'd also need to implement that pusher. And so each of those are also returning interfaces. This is what the fetcher interface looks like. This has a single method here. It takes the descriptor object that was returned out of the resolve object and is able to use that to know how to retrieve whatever is being referenced. And this gets called a bunch of different times for a bunch of different descriptors. Typically, the first descriptor that is going to be returned by that resolve method is the one that's going to describe either the index or the manifest of the image. And then the content of that is going to describe the next descriptors that containerd needs to retrieve. So the things that relate to the configuration of the image as well as each of the individual layers. And the fetch method is going to get called once for each of those different objects. It returns a standard reader object, and that reader is basically going to hide whatever the networking implementation is from the thing that's going to read the image. So as long as you're able to implement your networking as a reader, you can have your own thing go on here. For the ECR resolver that we wrote, we have a fetcher and a reader that's able to retrieve layers in multiple parallel requests for different portions of the content. And just based on ECR's architecture, that ends up speeding up the image pull a lot. If you're going to push images, you need to implement the pusher. So this looks very similar to the fetcher. The difference here is that it's returning a writer instead of a reader. But the same thing applies, that the writer is the thing that's going to implement whatever networking or protocol implementation you want to do. And so you can have your own implementation here that does whatever you need it to do. In ECR, we actually have two different ones, one that relates just to the manifest of the image and one that relates to the arbitrary blobs, so the content and the layers. Before I move on, are there any questions on this? OK. I'm not going to stop too much for questions in the middle. I'm going to hold most of them for the end. But if you have something burning, please feel free to raise your hand. So we just talked about extensibility in the client library. I want to talk about extensibility in the containerd daemon itself. So the containerd daemon supports what I call command line or executable programs that are invoked by containerd in order to perform some well-defined task. And they conform to some convention that's specified there. And containerd has some different use cases for it, and those have different conventions around them. Things like runtimes and log forwarding. I want to dig into runtimes a little bit. So containerd delegates control of the actual running of containers to another program. And that runtime is able to handle the implementation of what makes a container happen. The runc implementation that's used by default implements Linux containers with the various Linux container primitives, cgroups and namespaces, seccomp, capabilities, so forth. But you don't have to do that. You can have your own runtime that does something different. So for example, at AWS, we have this virtual machine monitor called Firecracker that's meant for very lightweight micro VMs. And we were able to implement a runtime for containerd that runs containers inside these VMs. And we're able to do that by conforming to the interface that containerd specifies. And you can see here there's two different interfaces up here. The one that's used by runc, which is the OCI standard, specifies things like the command line arguments, the working directory, files that are expected to be processed. And then there's the containerd v2 version of that, which specifies all those and in addition has an API that you're expected to expose on a Unix domain socket. So how do you build one? The first thing that you're going to do is you're going to build a binary, and that binary needs to be prefixed with containerd-shim-. And that's just something that containerd is going to look for, a binary conforming to that name. It does this primarily to make it so that when you're examining processes on your system, you can figure out which one is the container runtime. You're going to locate that binary in the search path. When you go and run them, containerd doesn't allow you to specify the full file path of the binary, but you just specify the name of the runtime, and containerd will transform that into the name of the binary and look for that on the path. You need to support a couple different command line arguments, things like start to start up a new container and delete to go and delete one. And there's some semantics around how those command line arguments are expected to be processed. So when you go and start a container with these container runtimes, it's expected to write out to its standard out a file path where the API that it's exposing is listening. There's some really nice properties around this model because this means that the container runtime is in control of its own decisions for how it wants to architect things. For example, if it wants to run a separate container runtime process for every container, or if you want to run one container runtime process for all containers, or if you want to group them together by some means, the way that you indicate that is choosing which socket to return. So if you want a brand new process for every container, you just return a new socket for everything. If you want to share, you return an address for a socket that's already existing. And then there's a command line argument for delete where you want to clean up the resources that are used by the container. And the thing that you need to expose over that socket is an interface called the task service. This is one of containerd's, the surface areas of one of the APIs. And this is how containerd controls the containers that are going to run there. So this is what that interface looks like. I've cut out a few methods, but it's a pretty long interface. All of these things correspond to different parts of the container lifecycle and the container runtime lifecycle. Some important ones relate to just how do you create a container. There's an API called create that lets you specify things like the root file system that the container is going to use and standard I/O and a bunch of other options. There's a start method where you want to actually start the process that corresponds to that container. There's a wait method that's available to wait for a process to exit, and so forth. One of the good things about implementing these, though, even though it sounds like a ton of work, there's actually helpers to make it really easy. So these helpers handle things like processing the command line arguments for you, allocating and starting up the service on that API socket, and lets you just focus primarily on your implementation of the interface rather than focusing on the mechanics around how do I get it running. So this is a little bit of what the code would look like to build your own runtime adhering to this interface. There's a main method at the top, and then there's a little helper in there called shim.run. And that's the helper library that containerd is providing to you that takes care of all that stuff. And the only thing that you're going to do is provide your implementation. There's that thing called myshim there. It's the function that returns your implementation of the task service, and you can make that do whatever you want. So once you've built the runtime, you probably want to test it out. The main way that you're going to interact with containerd is via its API or the client library. But when you're developing and you haven't necessarily built your client or you want to test with different clients, there's a development helper called CTR, and you can use this to go and test your runtime as well. And so this has a -- runtime argument that you can specify the name of your runtime. Containerd is then going to search the path, find it, execute it, wait for the socket to be available, and run against the API. So that's executable plugins. Next thing that I want to talk about is the gRPC proxy plugins. These are very similar to runtime plugins in that you're going to have a separate program that's responsible for implementing some sort of functionality. The difference here is the different parts of the API that are able to be supported, as well as these are not expected to have a lifetime that's controlled by containerd. Typically, you're going to run the process ahead of time and configure containerd with the address of the API that it's going to talk to. So there's a couple different types of proxy plugins, just the snapshotter and the content store. We're going to talk about snapshotters today. If you remember at the beginning we were talking about images and layers, snapshotters are the part that's actually responsible for making the unioning happen, making the copy on write functionality work. There's a bunch of different ways to do that, different implementations that trade off things like speed or space efficiency, or working well with large files, or working well with a lot of small files. Those can be things like the overlay snapshotter that uses the Linux overlay file system to just make files appear as a union together that are stored in different directories. You can have things that are file system specific, like the Btrfs or the ZFS snapshotters that are using native features of those file systems. Or you can use something that pretends to be a block device, like device mapper and LVM. So when we were building firecracker-containerd, the runtime for running micro-VMs in containers, or running containers in micro-VMs, we were able to implement our own snapshotter as a block device-based snapshotter out of process in a gRPC proxy plugin. That snapshotter was later contributed upstream to containerd, and the amount of work to convert something that was out of process to something that's native in process was actually fairly minimal. So what does it look like to go and implement your own? Again, there's an interface that you're going to need to implement. This is the snapshotter interface this time. And there's some helper packages for containerd that are going to make it pretty easy to do that again. This is what the interface looks like. This is the thing that you're going to implement to make your own snapshotter. This one's a lot shorter than the other interface I showed earlier, so these are all of the different functions that are there. A couple things to look at. One is called prepare. This is responsible for creating a new snapshot or creating a new layer and making it available for reading or writing. This is going to return a set of mount commands that containerd can run in order to get access to whatever's to write access into that snapshotter. There's commit that is used for sealing the snapshot once it's been written. And so once a snapshot has been committed, it's not expected to be changed again. Then committed snapshots are able to be used as parents for the prepare call. And so you can have a series of snapshots on top of each other. And this is what happens when layers are unpacked. So you'll unpack the base layer, you'll commit that, then you'll prepare a new snapshot from that base layer, unpack the second one, commit it, and so forth. This is also called when you're going to go ahead and run a container, because you want to create the new empty read-write layer that the container is going to use. And so containerd will call the prepare function again and get a new writable snapshot that's available for the container. You need to configure containerd to know about where to find the address for the plugin that you're going to use. And that looks like this. This is the configuration file that containerd uses. It's a toml formatted file located in the etc containerd config.toml file. And you can see here that you're specifying the name of the plugin, the type of the plugin, and the address where the API is exposed. And again, you probably want to be able to use this. So Typically, you're going to use it through the client library or the API, but when you're developing, you might want to use this CTR tool, and there's a -- snapshot or argument that lets you specify that you want to use that. So there's also Go plugins, dynamically linked Go plugins, and this is a functionality that's in the Go programming language itself, and Containerd just built support to import those plugins. It lets you add code into the main Containerd executable without having to build your own copy of it, and so it makes it really powerful to let you do really fun, interesting things there. But there's a bunch of complications around it, and these, some of which are similar to pretty much any kind of shared object or dynamically loaded library, things like needing to be architecture specific and operating system specific. But there's also some things in here that are difficult just because of the Go programming language, and those are things related to needing to use basically the same build environment to build the main binary and your plugin. That's because the versions of the compiler needs to match exactly, the versions of the standard library need to match exactly, and all of the libraries that are shared between your plugin and the main application that you're trying to load it into need to be the same. This has to do with like symbol resolution between the different binaries. They have to have the same, they have to be able to resolve the same symbols. So we tried to do this for firecracker-containerd. We have an API that we wanted to implement on top of the Containerd socket, and we tried to do that using a dynamically linked Go plugin, and we found that the complications with Go involved in dynamically linked objects just makes it really difficult to do. So instead, we did a built-in plugin. This is the last bit of extensibility that Containerd has, the last bit I'm going to talk about right now. So this is responsible for when you want to build your own version of a Containerd of Containerd. And there's pretty much all of Containerd's functionality is actually modeled as these built-in plugins. So the modularity of Containerd extends into the core itself. There's about 30 embedded plugins in the 1.3 release of Containerd. And those are things like the default implementations of the snapshotters and the default implementations of the shims to talk to the runtimes, various components for orchestrating different parts. And every component can be extended, replaced, removed. The downside is that it requires you to build your own binary. The good thing about it, though, is that just like Containerd's made other extension points really easy, it's made it really easy to build your own binary that doesn't involve you forking Containerd. Instead, because all of Containerd's functionality is pretty much these plugins, and they're all exposed as Go packages, you can treat Containerd as a library. And you can basically write your own main function, import all of the things, and then you have your own version of Containerd that has your own mix of what things are supported. I like to call this a distribution of Containerd. So how you do that is you're going to write your own main function, and you're going to hook into Containerd's plugin system, and this is what it would look like. Here's a main function. I've got the command.app thing that I've imported from Containerd, and that's the plugin system that's responsible for loading and running all of the plugins. Then you're going to import all of the things that you want to load into it, and these are imported as Go plugins, or as Go packages. So there's a pretty long list of what the existing ones look like. You're probably going to want to use most of these. If you look pretty closely, you can see that there's some of the things that we've talked about. So the content store is on here. There's also an images thing that deals with metadata around the images. This is about half the list, and the other half is over here. And this also has some of the things that we talked about. There's the snapshot service in here. And you can see at the bottom, I've imported my own into it. And so I can have my own plugin that is also imported in the same mechanism. If you look at the way that these imports are, and if you're familiar with Go, you can see that all of these are imported as underscore plugins. Go enforces that when you're importing packages that you reference the symbols in them, except when you import them as underscore packages. And that means basically you're importing it for the side effects. So what do I mean by side effects? Well, Go lets you specify a special function called init that runs at the time that the package is imported instead of being called directly. So the nature of all of these things being underscore imports means that the init function is going to run. And so you'll want to write your own init function that handles registering your plugin with Containerd. And this is what it would look like to do that. So here's my init function, and I'm going to call Containerd's plugin.register API and specify things like what is the name of my plugin, what is the type of the plugin, do I have dependencies, as well as yet another init function embedded in here. And containerd will take care of making sure that all of your dependencies are imported and running before it calls your init function here. So this is basically it for how you do that. So the next thing that I have is a little bit of a demo. And let's see what goes on here. So can everyone read this? OK. Just going to flip to my notes. So I have here just an EC2 instance that's been loaded with a couple things. So it's been loaded with containerd, it's been loaded with the various extension points that we've been talking about for doing things with ECR and doing things with Firecracker. Oh, I should maybe start the demo. So if we look here, we can see these are the different things that are available on there. You can see that there's firecracker-containerd listed there. That's my custom distribution of containerd. I've also got something there called ECR pull that's going to be responsible for pulling images using the resolver that we wrote. There's that CTR command line tool that is just basically a debug and development helper for containerd. And I've got a couple of these containerd shim binaries, some that correspond to runc, and one that is listed as Firecracker, and that's the one that uses the implementation that we've written. And I'll show you a little bit about how we've configured containerd. So it looks pretty much like a regular containerd configuration, except that I've told it where to store its state and where to expose its socket, and also that I'm going to use the device mapper snapshotter by default. This is the one that we had originally written as an out-of-process gRPC plugin, but now it's built in, and so I can reference it just like this without having to specify its socket. And what I'm going to do now is I'm going to look at the images that are present. This is just using the CTR command line tool, and we can see that there are no images. So I want to go ahead and pull one. And I'm going to use that ECR pull binary. This is using containerd's API to go and pull the images. So it's that pull function that we looked at before. And it's also got our special resolver that knows how to pull from the ECR API instead of from the Docker API. And we can go ahead and pull that. And then it gets unpacked. And we'll go ahead and look at this again. And you can see, even though I'm using the CTR tool and I use the ECR pull tool, they're basically showing the same content. So the CTR tool now shows the image that we pulled. And let's see what it looks like to run it. So if you're familiar with containers, I want to show you a little bit about what the host looks like and what it's going to look like inside of a container. So the first thing we're going to do is I'm going to show you about the host. You can see this is a Linux kernel. It's got a host name that looks like an EC2 instance because it's an EC2 instance. It has the Debian Cloud kernel loaded onto it. It's also, the OS release file tells me that this is a Debian instance. And so what we're going to do is we're going to run a regular container, a regular Linux container first on top of this and use the Amazon Linux image. And we're going to look at the same things. So we look at this again, and you can see it's the same host name, it's the same kernel. It's actually shared, and it says it's Debian, even though this is an Amazon Linux image. I promise I'm a faster typer when I use two hands, but I'm holding the mic. And then you can see here that this is reporting an Amazon Linux image. So this, if you're familiar with containers, you know that they typically share a kernel, and they're just running as processes in a user land on top of that kernel. So this shows us that we're running the Amazon Linux user land on top of the Debian kernel, which is what I would expect from a normal Linux container. So we'll get out of that, and then we're going to do basically the same thing, but we're going to specify our custom runtime here that runs it inside of a Firecracker micro VM. And so we've started up a virtual machine now, and we should see something a little bit different. And you can see that I've got something different here. I have a different host name that's reported. I've got a completely different kernel version that's reported. And this is showing me that this is the Amazon Linux kernel, not the Debian kernel. So even though I'm using a Debian host, I'm running a virtual machine inside of that, and then I'm running a container inside of that. And we can look again to see what the OS release file looks like. And this is going to show you the same thing that we saw in the image before. So it's still a regular container. It looks like a regular container, and it's just running inside of a virtual machine using the custom runtime that we wrote to extend containerd. OK, so you can see what it looks like inside the container. Now I want to show you a little bit about what it would look like to run a regular container and then a Firecracker VM with a container inside on the same host. So we're going to start up one of these again. This is, again, a regular Linux container, not using our custom runtime, and it's just running sleep in the background. And so when you run containers on Linux, you can typically see the process that's running, and so we should see a sleep process here. And we can go look at the processes that are related to this one. And you can see that this is a sleep process, and it's got some namespaces associated with it, and it's running under the containerd shim. This is the thing that's implementing the runc stuff, and that's parented under systemd right now. It's just related to the process model that's used for that particular implementation. So we'll go ahead and kill this, and then we're going to do the same thing, but we're going to run it inside of our custom runtime, inside of Firecracker. And so this is, again, going to start up a virtual machine. And I actually wouldn't expect to see the sleep process now, and I don't. Instead, what I can look for is the firecracker-containerd process. This is our distribution of containerd, and I can look at the process tree that's associated with that. And now you actually see that under this are some Firecracker processes and a containerd shim that corresponds to the Firecracker process instead of the runc process. And so that's pretty much what the demo looks like. Recap of this, we just showed a couple of extension things with containerd where you can write your own resolver and you can pull images not using the default one. We showed that we have a custom containerd binary, a custom distribution of that with some extra functionality built into it. We showed the device mapper plugin. That's the thing that uses block devices, and that was just used for in our containerd configuration file. And we showed the containerd shim, the implementation of the runtime used for micro-VMs. And so at this time, I'm happy to take questions. So I'm going to try and repeat questions because I think we only have one mic. And so I am going to ask you to speak up so that I can hear you up here. But for anyone that didn't hear, the question was about whether you can run privileged containers inside Firecracker, Firecracker containerd. So yes, this is it runs a Firecracker containerd runs by running a virtual machine and then running containers inside of it. And so you can run containers that are privileged in the context of that virtual machine. And so they can have full control over the host as if they were, because they just see the virtual machine instead of seeing the outer host.